So today we have our book BSc Inorganic Chemistry, Volume 2nd, written by Dr. K. Bhasin, और इसका फर्स्ट चैप्टर है केमिस्ट्री ऑफ एलिमेंट्स ऑफ फर्स्ट ट्रांजिशन सीरीज. Transition element constitute a large block of elements in the central part of periodic table. Periodic table का जो central most part होता है constitute करते हैं transition elements. These elements are surrounded by S block element on the left side and P block element on the right side in the periodic table. All the transition elements are metals and find numerous useful applications. For example, iron is extensively used in heavy machinery and building materials. Gold, silver, and platinum are precious metals and highly prized for their beautiful appearance and rarity. Copper, nickel, and zinc are well known for their use in coins since early civilizations. Many transition elements are of biological importance. For example, iron present in hemoglobin is responsible for the transfer of oxygen from the lungs to other body tissues. Cobalt is the central element in vitamin B12. Molybdenum, iron together with sulfur constitute a versatile biological catalyst that is used to convert atmospheric nitrogen to ammonia. A number of catalysts for the industrial production of chemicals involve transition elements. Compounds of transition elements are found in every color of the rainbow. Colored transition metal compounds make them useful as pigments in paints and dyes. In this chapter, we will focus on the general properties of all the transition elements, but with special reference to transition elements of fourth period. All the 114 elements known till date have been grouped together in four blocks. They have been grouped together in four blocks that are S, P, D, and F block. The grouping of elements has been done on the basis of last electron received in the valence shell of atom. Thus, alkali metals, that is lithium to francium, with a half-filled outer subshell, together with alkaline earth metals, that is beryllium to radium, with filled S subshell, comprise the S block elements. Similarly, element with partly or fully filled outer p subshell comprise the p block elements. It means that p block elements consists of element from boron through neon down to thallium through radon. S and p block elements taken together comprise the main group elements. Between the S and p block elements, there are two additional blocks of elements in which the last electron enters either d or f orbitals. The group of elements in which the last electron enters the d orbital is called d block, whereas the group of elements in which last electron enters the f block is called f block. In the short compact form of periodic table, the f block elements are conveniently placed beneath the remainder of the periodic table. The elements within the D block are generally called transition metals, whereas elements in the F block are called inner transition elements, because these elements are inside the transition series of elements. Chemists generally restrict the term transition metals to come, but not all of the D block elements. Strictly speaking, the D block elements are defined as those elements which have partly filled D subshell either in the elementary form or in their commonly occurring oxidation state. It means that the term transition applies to an element with a partly filled D subshell, and this excludes those with D0 or D10 configurations. However, it is convenient to include copper, silver, and gold in the classification, as these elements commonly form ions with partly filled d subshell. Although the neutral atoms have d10 electronic configurations, it is the chemistry of their ions which is of primary interest. You can see in figure 1.1, this is a periodic table with elements usually defined as transition metals are shown in black and post-actinoid metals are shaded. However, according to the above definition, elements of group 12, that is second B, zinc, cadmium, and mercury are excluded from the transition elements. This is because these elements not only in their elementary form but also in their dicationic form have d10 electronic configuration. In other words, these elements do not show major similarities in the properties to other transition elements except for their ability to form complexes with ligands. Species capable of donating a pair of electrons such as water, ammonia, halide ions. Despite the poor similarities in properties with other transition elements, elements of group 12 are quite often considered together with the transition elements. In fact, zinc, cadmium, and mercury constitute the last members of D block series. The transition elements are spread over 4 rows, that is periods. These rows are called first, second, third, and fourth transition series, depending upon the filling of 3D, 4D, 5D, 6D orbitals. We know that there are 5D orbitals in a given shell, and each one orbital can accommodate up to 2 electrons. Thus, there are 10 elements in each row of the D block. The first, second, and third transition series contain complete rows of 10 elements, whereas the fourth transition series is incomplete. The elements from scandium to zinc constitute first transition series. The elements from yttrium to cadmium constitute the second transition series. The elements from lanthanum, hafnium, and to mercury constitute the third transition series. First transition series, fourth period, that is scandium to zinc, 3D orbitals are gradually filled. Second transition series, fifth period, yttrium to cadmium, 4D orbitals are gradually filled. Third transition series, sixth period, lanthanum, hafnium, mercury, 5D orbitals are gradually filled. Fourth transition series, that is seventh period, actinium, rutherfordium, dubnium, seaborgium, borium, hessium, meitnerium, 6D orbitals are gradually filled. Position of D block elements in the periodic table. D block elements or transition elements occupies the central position in the periodic table in between the S and P block elements. S block elements are well known to form ionic compounds, whereas the metallic elements of P block show a very high degree of covalent bonding. This transition, that is change from predominantly ionic to covalent character, becomes significant in case of central elements while progressing from group 4 to group 11. This is the main reason why D block elements is assigned as an alternative name, that is the transition elements. In order to discuss the position of transition elements in the periodic table, we may consider the filling of atomic orbitals with the increment in atomic number, the variation of the energies of atomic orbitals with increasing atomic number in neutral atoms are shown. In case of hydrogen atom, the order of increasing energy for the atomic orbitals is determined by the value of principal quantum number n. The energy of the electron is the same irrespective of whether it is in s, p, d or f orbital, as long as the principal quantum number n is the same as shown. For example, in the fourth principal shell, all 4s, 4p, 4d and 4f subshells have the same energy. However, this is not true for atoms with more than 1 electrons. The nucleus of many electron atom is more highly charged than the hydrogen nucleus, so it attracts the electrons more strongly and hence lowers their energy. However, the electrons also repel one another and raises their energy. Thus, the differences in energy of orbitals in different subshells of the same shell is due to the combined effect of attraction between electrons and the nucleus, and the repulsions between the electrons. As a result, the electron is less tightly bound to the nucleus than it would be if other electrons were present. In case of multi-electron atoms, it is observed that the various subshells, that is SPDF, in the same principal shell split apart into different levels. Furthermore, on moving from one electron system to multi-electron system, the energies of all the levels drop to lower values. This decrease in energy can be attributed to the repulsive interaction of electrons in the polyelectronic atoms. An electron, we know, is held in its atomic orbital by the Coulombic attraction of the nuclear charge. But when more than one electron is present in a system, the two electrons repel each other and destabilize the system. This repulsion can be interpreted in terms of one electron shielding the other electron from the effect of nucleus. In other words, each electron is shielded from the full attraction of the nucleus by the other electron in the atom. The shielding effectively reduces the pull of the nucleus on the electron. This leads to the concept of effective nuclear charge, Z effective, which is the nuclear charge actually experienced by the electron. The effective nuclear charge experienced by the electron is always less than the actual charge because the electron-electron repulsion work against the pull of the nucleus. Thus, the lowering of energies of all levels is due to the increase in the magnitude of effective nuclear charge, which in turn is due to the inefficient shielding of an electron in a particular orbital, while all other electrons in the atom. It is also important to note that the energies of various subshells do not drop in a regular manner. Instead, the drop in energies of various subshells occur in a regular way. This is because different subshells in the same principal shell are shielded to different extents due to different shapes. An s electron of any subshell can be found very close to the nucleus, so we say that it can penetrate through the inner shells. A p or electron penetrates to a smaller extent. This means that p electrons are more effectively shielded from the nucleus than the s electrons. Similarly, the d electrons are bounded less tightly than the p electrons in the same shell. The order of shielding effect of an electron in different orbitals is s, then p, then d, and then f. Close inspection of figure 1.2 reveals that the filling of electrons in orbitals occur in the sequence 1s, 2s, 3s, 3p in all the atoms. In building up electrons from the hydrogen to argon, filling of electrons follow the above sequence. During the filling of these orbitals, the energies of higher unfilled orbitals are affected by screening power of these 18 electrons. In argon, 3s and 3p orbitals are completely filled, and it is expected that the next electron, in case of potassium, may enter the 3d subshell. However, we know that potassium belongs to S block. As a result, the next electron after argon prefers to go to 4s instead of 3d. This can be explained in terms of the different extents to which the outermost electron penetrates the charge cloud of the low-lying electrons. Different subshells have different penetration powers, and the orbital that penetrates more to the nucleus will be less shielded from other electrons and is pulled more towards the nucleus. As a result of increased nuclear pull, the electron will have lower energy. The degree of penetration of electrons in a given principal shell decreases in the order SPD and then F. The penetration power of 4s electron is greater than the 3d. As a result, the energies of 4s is lower than that of 3d subshell. This can be easily understood from the radial distribution curves of 3d and 4s orbitals. Of the 3d and 4s, the 4s orbitals has 4 to 1, that is 3 small concentric spheres, and underneath the main 4s subshell. Although the inner spheres carry only a small probability of finding the electrons, it is also important to note that 4s orbital spreads out into space more than the 3d orbital. Thus, the 4s orbital, being more penetrating, experience the more positive nuclear than the 3d orbital. As a result, the energy of 4s orbital falls and make it more stable than the 3d orbital. Thus, in potassium and calcium, 4s orbital is occupied in preference to 3d. In building the element from hydrogen to calcium, the unoccupied 3d filled subshell is effectively shielded from the increased nuclear charge by the electrons of argon core. This results in the energy of 3d orbitals fairly constant. In contrast, the energies of 4s and 4p orbitals are declining. As they penetrate the argon core more, However, the 3d orbitals penetrate 4s and 4p, so that after calcium, a 3d orbital 3d electron is not fully shielded from the increasing nuclear charge by 4s subshell. Thus, by the time scandium is reached, the 3d subshell has fallen to an energy close to that of 4s. Electron in the d subshell shield one another from the nuclear charge poorly because the lobes of d orbitals on the same atom are relatively far apart from each other. As a result, the energy of 3d orbitals continue to fall with the increase in nuclear charge, and they drop to lower energy than 4s. The next electron in scandium enters 3d subshell. Thus, the electronic configuration of scandium is: a 3d electron in scandium screens the 4p subshell more effectively than it screens the remaining 3d orbitals. As a result, the incoming electrons prefer to enter the low energy 3d orbital from titanium to zinc till the entire 3d subshell is completely filled. Thus, zinc with atomic number 30 has electronic configuration. The element from scandium to zinc involving the filling of 3d subshell constitute the first transition series. After the completion of first transition series, the filled 3d subshell has fallen well below the 4p subshells in energy. It is no longer part of the valence shell but has become a core subshell because 3d shell sits inside the 4s subshell. Thus, by the time gallium is reached, 4p subshell becomes lowest in energy, and therefore the next 6 elements up to krypton are filled in the 4p subshell. The electronic configuration of krypton completes the 4p subshell and is krypton is equal to 1s2 2s2 2p6 3s2 3p6 4s2 3d10 4p6. After krypton, the filling of electrons in different subshells occurs in the same way as we have observed at argon. This pattern is repeated with 5s, 4d, and 5p. As observed in case of 3d subshells, the 4d subshells are higher in energy than 5s because of the shielding effect. As a result, the filling of next two elements, rubidium and strontium, occurs in 5s. After the filling of 5s subshell, 4d subshell is lower in energy than the 5p, and therefore the second transition series begins at yttrium and completes with cadmium through 8 other elements of the second transition series, that is zirconium, niobium, molybdenum, technetium, ruthenium, rhodium, palladium. After the complete filling of 4d, 5p subshell becomes lowest in energy, and the next 6 elements up to xenon involving the filling of 5p subshell. The electronic configuration of xenon is therefore 1s2 2s2 2p6 3s2 3p6 4s2 3d10 4p6 5s2 4d6 4d10 5p6. After xenon, the filling of next two electrons elements cesium and barium occurs in 6 subshell as 6s1 and 6s2 respectively. After the filling of barium, and the 4d 5d and 6s have converged in energy, the 6s orbital is not effective in shielding the 4f and 5d electrons. As a result, 4f and 5d electrons experience the nuclear pull more, and their energies decrease abruptly and become nearly similar. The next entering electron in the element lanthanum enters the 5d orbital and marks the beginning of third transition series. The electronic configuration of lanthanum is: question number 1. Why an ns orbital for any row are used before n-1d or n-2f? The ns orbitals for any row are filled first because the radial portion of the wave function for an s orbital is distinctly closer to the nucleus than the wave function of d and f orbitals. The n-1d orbitals are higher in energy than the higher in energy than an s orbital for certain elements. Consequently, however, after lanthanum, the next element starting from cerium to lutetium involve filling of 4f orbitals as shown below. Elements from cerium to lutetium involving the filling of 4f orbitals are lanthanides and constitute a part of separate block beneath short form of periodic table called F block. After lutetium, next electron enters 5d and constitute filling till the 5d subshell completely filled. In the process of filling 5D, elements starting from hafnium to mercury complete third transition series. The electronic configuration of hafnium and mercury are given. After mercury, next six elements involving the filling of 6p orbitals till the element radon is reached. After radon, the next two elements francium and radium involving filling of 7s orbitals. Once radium is reached at Z is equal to 80, the 5f, 6d and 7s subshell converge again in energy. The 7s orbital is not effective in shielding the 6d and 5f orbitals. As a result, 6d and 5p experience more nuclear pull because of penetration power, and their energies fall substantially fall below 7s. Energies of 6d and 5f are nearly similar in magnitude. Next entering electron in the element actinium enters 6d subshell, thereby making the beginning of sixth transition series. If you recall, the sixth transition series is the only incomplete D transition series. The electronic configuration of actinium is, however, after actinium, the next element starting from thorium to lawrencium involve filling of 5f orbitals. This is because the 5f subshell penetrates the 6s and 6p subshell and is not shielded well from their nuclear charge. Consequently, the energies of 5f orbitals decrease considerably. Electronic configurations of thorium and lawrencium are: the elements from thorium to lawrencium that involve the filling of 5f orbitals are known as actinides, and this constitute a part of the separate block beneath the short compact form of periodic table called F block. After lawrencium, the next electron enters 6d subshell. As in case of actinium, elements appearing after actinides are commonly known as post-actinoids. Up to now, since 9 post-actinoid elements have been synthesized, however, their short lives have made it very difficult to study their chemistry. Some of the post-actinoid elements have been recently named as Rutherfordium, dubnium, seaborgium, borium, hessium, technetium. Naming of these elements have always remained under the cloud of controversies. This is because all the three nuclear faculties, that is Berkeley in California, Dubna in Russia, Darmstadt in Germany, have simultaneously claimed the first synthesis of each of these elements. For example, the first discovery of element 104 was claimed by Berkeley and Dubna groups, the former naming the element Rutherfordium and the later Kurchatovium. In order to settle the conflicting reports, IUPAC devised a hybrid Latin-Greek numerical method of providing provisional names and symbols for the newly discovered elements. Now name an element in the periodic table that was named after the name of scientist when he was alive. Traditionally, no element is named after a living scientist. However, only one element has been named. When the scientist was alive, it is seaborgium after the name of nuclear scientist Glenn Seaborg. So now coming to the electronic configuration of D block elements. Electrons are assigned to an atom by placing them into various atomic orbitals according to three rules, that is of Poe, that is Hund's, and the Pauli exclusion. If these rules are followed in assigning the electrons to various atomic orbitals, the assigned electronic configuration is the ground state. Filling of electrons in first, second, and third period is simple and straightforward and only requires the appropriate S and P orbitals. However, the filling of electrons in the fourth, fifth, sixth, and seventh period require D or F subshell in addition to S and P. Elements whose atoms involving filling of D subshells are called transition metals, whereas elements whose atoms involve filling of F subshells are sometimes called inner transition elements, or more usually called lanthanides and actinides. Position of D block elements can be better described by considering the combined effect of attraction between the electrons and the nucleus, the repulsion between the electrons in different Mutual screening effect of the orbitals and magnitude of nuclear charge. For a given period, the transition elements are always preceded by two elements. 2s block coding the general electronic configuration for atoms of d block may be written as n-1 d1 sit n, ns1 sit 1 or 2. N is the outermost shell while n-1 is the penultimate shell. Accordingly, scandium, the first transition element, has the configuration that is scandium. The electronic configuration of all other elements in the first transition series are tabulated in table 1.1. Following scandium, the 3d orbitals are filled up more and more till the last element, zinc, is reached, where the 3d orbitals are completely filled. The expected electronic configuration of chromium is argon 18 3d4 4s2. However, the actual configuration has one electron assigned to each of the 5 available 3d and one electron to 4s orbital. This is explained by assuming that the 4s and 3d orbitals have approximately the same energy at this point, thus giving rise to 6 orbitals of nearly the same energy. Each of the 6 valence electrons of chromium is assigned a separate orbital. This ensures less repulsion and ease and hence increased stability. It can also be explained on the basis of conventional exchange theory, conventional exchange energy. Similarly, argument applies in the case of copper, where the electronic configuration of copper is argon 18 3d10 4s1 instead of argon 18 3d9 4s2. Students are advised to recapitulate the half-filled and completely filled electronic configuration D5 and D10 are associated with extra stability. Second transition series. The second transition series is comprised of elements from yttrium to cadmium. It involves the filling of 4d orbital in the fifth period as described. Compared to first transition series, the electronic configuration of second transition series is not straightforward to explain except in cases of molybdenum and silver, where d orbitals are half filled or completely filled. In order to account for the anomalous behavior, various types of interactions such as nuclear attraction, electron repulsion, penetration, mutual screening of orbitals have to be taken into consideration. Third transition series. The first element of the sixth period is lanthanum with the electronic configuration that is xenon 54 5d1 6s2. Next 14 elements from cerium to lutetium are assigned 4f orbitals. After lutetium, the next 9 elements from hafnium to mercury involve gradual filling of 5d. Thus, the element lanthanum, hafnium to mercury, totaling 10, belongs to 3d third transition series. Like second transition series, the predictions of electronic configurations of a particular atom of third transition series is fairly difficult. Third transition series differ from the first and second transition series as it also includes an additional group of 14 elements called the lanthanides. Fourth transition series, this series is incomplete compared to the first three transition series, which are complete with 10 elements each. This series involves the gradual filling of 60 orbitals starting from actinium. The electronic configuration of actinium and rest of the known elements are tabulated below. Cation is formed from the neutral atom by the removal of one or more valence electrons. If the principal quantum number of the valence shell is n, then np electrons are lost first because p subshell has the highest energy. Once np electrons have been removed, then ns electrons are lost, and finally the appropriate number of d electrons are lost of the previous shell, if any. For example, in case of iron, the electronic configuration is in case of ferric ion, since there are no 4p electrons, so the first 2 electrons are removed from 4s. Third electrons comes from the 3d. Thus, the electronic configuration of ferric becomes this. All common transition metal cations have the electronic configuration of general type. that is noble gas score n-1 dx. It is important to remember this because the chemical and physical properties of transition metal cations are determined by the presence of electrons in d orbitals. One should be very careful in writing the electronic configuration of atoms while predicting the charge on the corresponding ions. The series of elements, that is nickel, palladium, platinum, illustrate this point. This electronic configuration of these elements as atoms are different, although the ionic charges and their electronic configurations are similar. Collections of elements in d block elements are called transition elements. They are especially called transition element because their properties marks a transition between highly reactive metallic element of S block, which form distinctly ionic compound, and the elements of P block, which form largely covalent compounds. All the D block elements are metals. Some of the general characteristics of D block elements are summarized. All the transition metals are hard, except for group 11, and have very high melting and boiling points. Nearly 10 transition elements have melting point above 2000, and 3 elements, tantalum, tungsten, and rhenium, have melting points above 3000. They are hard, strong, refractory, electropositive. Transition elements all have high density. Osmium and iridium have densities of order 23 gram upon centimeter cube. Most of the transition metals are malleable, means that they can be reshaped on hammering, and ductile means they can be drawn out in wires. Most of the transition metals are good electrical conductor. These elements form colored compound of every color of the rainbow. These elements forms alloys with other metals. These elements are well known to form coordination complexes. Most of the transition metals and their compounds are used as versatile catalysts. Most of the transition metals forms paramagnetic compounds. Transition metals exhibit several oxidation states. Transition metals in general are comparatively unreactive. Only a few metals such as iron are electropositive to react with acids. Transition elements have a number of properties that distinguish them from main group elements. It is probably because the addition of electrons in case of transition metals takes place in the penultimate shell next to outermost and not in the outermost. In case of main group elements, the addition of electrons takes place in the outermost shell. Let us evaluate how the important periodic properties varies in case of transition elements. In order to explain the chemistry of transition elements, it is first necessary to consider some of the atomic properties and later to know how these influence in binding of its valence electrons. Electron clouds, if you recall, do not have sharp boundaries. However, when atoms pack together in solid and in molecules, their centers are found at definite distances from each other. The atomic radius of an element is defined as half the distance between the centers of neighboring atoms. In case of copper metal, the distances between two neighboring nuclei in the solid state is 2.56 angstrom. Therefore, the atomic radius of copper is 2.56 upon 2, that is 1.28 angstrom. The variation in the atomic radii in case of transition metals is not as regular as observed in case of main group elements. S and P block elements. The atomic radii of the elements decrease from left to right across a row in the transition series. This is because on moving from left to right in the D block element, the addition of electron takes place in the n-1 subshell, which adds to the primary screening effect. The additional electron screens the outer ns electrons effectively from the added nuclear charge. As a result, with the increase in the atomic number, the screening effect also increases considerably. This results in the increase of effective nuclear charge only marginally, and hence there occurs only a small increase in the atomic radii. It has been observed that the atomic radii of first transition series decreases gradually from scandium to chromium, but remain practically constant from chromium to nickel. However, towards the end of the first transition series, there is an increase in the atomic radii. This increase in the size can be attributed to the increased electron-electron repulsion due to added electrons in comparison with the attractive forces due to increased nuclear charge. A similar behavior in the atomic radii has been found in case of second and third transition series. There is an increase in the atomic radii in going from fourth period to fifth period elements within any column. It is important to note that this increase is not significant in going down the group in case of S&P block elements. For example, in going down to group 11 elements, the covalent radius of scandium is 1.44 angstrom, that of yttrium is 1.62 angstrom, while that of lanthanum is 1.69 angstrom. This increase in the radius from 4th period to 5th and 6th period is due to the addition of a new shell of electrons. All the elements in the 6th period beyond lanthanum have nearly the same atomic radii as that of the corresponding element in the 5th period. This similarity in the radii in the 5th and 6th period transition elements can be explained in terms of lanthanide contraction. Densities of transition elements are very high compared to the alkali and alkaline earth metal. The atomic volumes of transition elements are smaller than the elements of alkali and alkaline earth metals. This is because the increased nuclear charge is very poorly screened by the intervening orbitals and consequently attracts the electrons more strongly. In addition, the added electrons occupy the inner transition elements. Due to decrease in atomic volume of transition metals, there is an increase in the density of transition metals. Although the overall change in radii among these metals is small, the effect is magnified because atomic volume is actually changing with the cube of radius as given below. So density is equal to mass upon volume, that is mass upon 4 by 3 pi r cube. An inspection of figure 1.6 reveals the trends in the densities of elements in a given series. The densities increases from period 4th elements to period 6 elements, with the highest values being those of osmium and iridium, and then decreases. This increase in the density is due to small radii and closed packed structure in the nearly central elements of the transition series. After group 8th, the densities of element again decrease. This is due to the increased repulsive forces operating between electrons in comparison to the attractive forces due to the increased nuclear charge in these elements. On going down the group, there is also a noticeable increase in density of elements as shown. We have already discussed that the atomic sizes of a corresponding second and third transition series remains practically the same, but their atomic masses becomes roughly twofold. Consequently, the densities of element of third transition series are nearly twice those of the corresponding element of the second transition series as shown in table. Name an element in the periodic table which has the maximum density. It is osmium with a density of 22.57 gram per upon centimeter cube. To appreciate the density of osmium, imagine a football made of osmium with 30 centimeter in diameter. Do you know how much will it weigh? It weighs 320 kg. Third property is melting and boiling points. Melting point is the temperature at which the crystal lattice of solid collapses and the solid is converted to a liquid, whereas the boiling point is the temperature at which the vapor pressure of a liquid becomes equal to the external pressure on the liquid. Melting and boiling point of a D block elements are generally very high. The metals with the high melting point are found in the middle elements of each series. The melting point of any substance reflects the forces of attraction between the atoms, molecules, or ions constituting the solid. In each transition metal series, the melting point rises to a maximum around the middle and then decreases. The melting point indicates that the metals are strongly held together by metallic bonding. The strength of metallic bonding is related to the number of unpaired electrons in the metal. The larger the number of unpaired electrons, the stronger is the metallic bonding. Consequently, higher is the melting point. At the beginning of a period of transition element, there is only one unpaired electron. The number of unpaired d electron increases across a period until group 6, after which the number of electrons begins to pair. Therefore, the melting point of transition metals decreases from 1540 degrees Celsius for scandium to 1900 degrees Celsius for vanadium and 1875 for chromium, then decreases from 1536 for iron to 1085 degrees Celsius for copper and 420 degrees Celsius for zinc. Same pattern of melting and boiling point along the transition series is observed in fifth and sixth periods elements. It is further important to note that the melting and boiling point increase on moving down the group. Thank you so much.